Hello everyone, I welcome you all to this digital classroom for the subject control systems. Today we are going to discuss about the new module, stability analysis, and we are going to get introduced with respect to the concepts of stability analysis. In the previous module, we have seen that every system needs a small amount of time to pass through a transient period. Now, let me put up a question that whether the system will reach to its intended steady state after passing through transient time or not. The answer to this question means to define whether the system is stable or unstable, and this is called as the stability analysis. The analysis of whether the given system can reach the steady state after passing through the transient successfully is called as stability of the system. So first, let's understand the concept of stability. Consider a system, an object here, a cone. Now if I apply a force on the object, it will oscillate and it settle down again to its original position. And such system is called as absolutely stable system. Now if I try to place an object in this position, the system keeps on oscillating when certain force is applied, and the system can neither be stable nor unstable, and hence we can call it as a marginally stable system or neutral system. Now let me try to fit this cone upside down, and in this case the object will fall down without any application of force. So if you try to keep it in this position, we will always fail to do so, and such system is called as an unstable system. Hence we have three types here: stable, neutral, and unstable system. So what will be the result of instability? Now look at this image. The first image shows the bridge which is in stable state, and on the other side the bridge has been completely collapsed due to instability. And it's very important to discuss about stability of a control system. So let us discuss about the stability of a control system. The stability of a linear closed loop system can be determined by the location of closed loop poles in the system. So let me consider a closed loop system as shown here with input as RFS and output as CFS. Then the transfer function is given by CFS by RFS is equal to GFS divided by 1 plus GFS into HFS. So we know that the denominator polynomial equated to 0, we can call it as a characteristic equation. Here we have the characteristic equation as 1 plus g of s into h of s is equal to 0. Now, substituting for j omega for s, we get 1 plus g of j omega into h of j omega, which is equal to 0. Now solving this equation, we get the roots. The roots will have two parts, one on imaginary and the other on real. The real part is denoted with sigma axis and the imaginary part is denoted with j omega axis in the S-plane. And for stability related to the location of poles, one can say that a system is stable if the poles lies in the left half of the S-plane, and it is unstable if it lies in the right half of the S-plane, and it is called as marginally stable if it lies in the imaginary axis. But how do we say that? The answer lies here with the question, what is the inverse Laplace transform of 1 by s minus 1 and 1 by s plus 1? So let us take few examples to justify the statement. So let me take a closed loop system. So let me consider the transfer function of a system given by CFS by RFS is equal to 1 by s plus 1 with impulse as input. Hence the Laplace transform of impulse is 1. Substituting for RFS is equal to 1 in the above equation, CFS will be equal to 1 by s plus 1. So equating the denominator equal to 0, we can call it as a characteristic equation and it gives you the location of the pole. And we have obtained s plus 1 is equal to 0, hence s is equal to minus 1. So we have a pole in the left half of the S-plane. So let us locate the pole, and now in the meantime let me take the inverse Laplace transform of C of S, which gives you C of t. So we know the Laplace transform equality 1 by s plus a implies e to the power of minus at. Here we have a is 1, hence it is of the form e to the power minus t. So now let us plot the pole in the S-plane and let us look into the response of C of t. So the roots are real and negative and it lies in the left half of the S-plane. Here we have a pole. We know the pole is represented in a cross mark and it is lying in the left half of the S-plane as s is equal to minus 1. And the response of the system is exponentially decaying in nature. For the pole which lies in the left half of the S-plane, the impulse response dies out to zero after a finite time, indicating a bounded output response. Or I can say that if the response is converging in nature, the system is said to be stable. Let me take another example in which CFS by RFS is equal to 1 by S with same impulse input, hence RFS is equal to 1. Substituting for RFS, we have obtained CFS is equal to 1 by S. So equating the denominator equal to 0, we have obtained S is equal to 0, which means we have one pole at the origin. And if you take the inverse Laplace transform of C of S is equal to 1 by S, we can obtain C of t, and inverse Laplace transform of 1 by S is 1 in this case. So let us look into the location of pole in the S-plane and its response. So we have one pole at the origin. We know that pole is represented in a cross mark, and we can look into the response on the other side. So for the pole at the origin, the impulse response is constant with time, indicating bounded output response. Hence, I can say that the system is absolutely stable. Moving on to the next example, for a given closed loop transfer function, C of S by R of S is equal to 1 by S minus 1 with input as impulse, hence R of S is equal to 1. Substituting for R of S in the above expression, we obtain C of S is equal to 1 by S minus 1, and equating the denominator S minus 1 is equal to 0, we get S is equal to 1, and taking the inverse Laplace transform, we have obtained C of t is equal to e to the power t. So now let us look into the location of this pole and its corresponding response. So we have one pole at the right half of the S-plane, and let us plot the response. So the response of the system is exponentially increasing towards infinity. When the roots are real and positive in the right half of the S-plane, the impulse response increases without any bound as time increases. Hence the system is unstable. So let us take another example. For a given closed loop transfer function C of S divided by R of S is equal to 1 by S square plus 1. Substituting for R of S, we have obtained 1 by S square plus 1. And if you equate the denominator equal to 0, we can obtain two roots, which is S is equal to plus or minus j. Hence the roots lie on the imaginary axis. And if you take the inverse Laplace transform, we can obtain C of t is equal to sin t. So let us plot the location of pole in the S-plane and let us look into the response C of t. So we have two poles on the imaginary axis, one plus j and the other is minus j. And if you look into the response of the system is oscillating in nature when the roots are on the imaginary axis. Hence, we can say that the system is marginally stable or critically stable. So we have few more conditions with respect to the poles located on the imaginary axis. The first condition is the presence of repeated poles on the imaginary axis makes the system unstable since the response becomes unbounded with increase in time. Whereas if one or more non-repeated roots of the characteristic equation are on the imaginary axis, then the response is bounded. Moving on to the next example, C of s by R of s is equal to 1 by s square plus 2s plus 2, and substituting for R of s as 1 and further simplification, we have obtained the denominator term as s plus 1 the whole square plus 1 is equal to 0. Now you have to iterate the denominator polynomial equal to 0, and we have obtained two roots as minus 1 plus j and minus 1 minus j. It clearly shows that the roots are complex conjugate. And let us take the inverse Laplace transform C of s, and we have obtained C of t as e to the power of minus t into sine t. So now let us locate the pole on the S plane and let us look into the response. So the response of the system is exponentially decreasing sinusoidal waveform, and it is trying to reach 0 when time increases. And for the roots which are complex conjugate with negative real part, the system is said to be absolutely stable. Moving on to the next example, on the other side, if the complex conjugate pole lie on the right half of the S-plane, the response will be completely diverging, that is unbounded response. It never try to converge and reach a 0. Hence, you can say that the response of the system is exponentially increasing sinusoidal waveform for the roots which are complex conjugate with positive real part on the right half of the S-plane, and the system is unstable. And I have consolidated all the response with respect to converging. We can say that the system is stable, and if it is diverging in nature, you can say that the system is unstable, and if it is oscillating in nature, you can say that the system is neutral. So with these examples, you have clearly understood about the concept of stability. Now with these examples, we have justified that if a pole is present in the left half of the S-plane, then the system is stable, and if it is present in the right half of the S-plane, then it is unstable, and if it is present on the imaginary axis, we can say that the system is marginally stable. Now it is very easy for you to define for bounded input and bounded output stability. That is, a system is stable if for every bounded input signal, the system response is also bounded. Then I can say that it to be as a stable system. Similarly, a system is unstable if for any bounded input, the system response is unbounded. Then we can say that the system is unstable. Now let us look into the history of RH criterion, which two independent historical paths leads to the stability criterion. Edward Routh's essay titled A Treatise on the Stability of a Given State of Motion contained the stability criterion, and on the other side, Routh-Hurwitz arrived the stability criterion independent of Routh's using a different method. To honor these independent efforts, their result is known as Routh-Hurwitz stability criterion. Now the question is it really possible and feasible for us to calculate the roots of every kind of higher order characteristic equation? The answer is definitely no. But then what is the solution? The answer is the Routh-Hurwitz criterion. Hence, the Routh-Hurwitz criterion is called a necessary and sufficient test of stability because a polynomial that satisfies the criterion is guaranteed to be stable. The criterion can also tell us how many poles are in the right half plane or on the imaginary axis. So in the next lecture, let us discuss about the necessary condition for stability and the Routh stability criterion. Thank you.